So just to mention, I have put up solutions to those overnight problems, hopefully correct ones, on the wiki. But any errors, there's a few bonus points if you find the errors in them. And I'm afraid I haven't checked through the two solutions that I've been handed in, so I'll try and do that this evening and let people know if they are okay. I'm sure they're good. So. The other thing, I've been asked to sort of show this book, so I'm going to show this book. This is Kernel Methods for Pattern Analysis, which is, again, co-authored with Nello Cristianini. It's just come out recently. And I just thought I'd mention that in there is a theoretical analysis of sort of the kernel approach. And what we've done is base it on the Radamaca complexity stuff that I'm talking about now. So if you're interested in a sort of more of a textbook treatment of that, it is contained in this new version. Whereas in the old book, there's a slightly more sketchy theoretical chapter which uses the covering number approach that I described yesterday for the large margin case, but not containing the overnight problem solution. Because that was not around at that point, so using the Allon et al. Approach. Okay, so I think we're now, I mean, this is really the core of where we got to before, the core of the sort of applicable theorem for Radamaca complexity. And perhaps just a word of philosophy. I mean, it's very interesting, you know. I mean, I was joking here when we were going through this proof, and I said, okay, this looks a bit tough. Well, let's just make it a definition. And in a way, I think this is part of the way Radamaca has succeeded. It stopped with a definition at the right moment. And in a sense, it said, okay, I've taken you this far in generality. Now you're going to have to go, if you want to go any further, you're going to have to do it with a specific function class in mind. And they've stopped at the right point in a sense. Maybe the VC dimension went too far in generality, and therefore you've lost, in a sense, the ability to take advantage of certain features of your particular function class because you're constrained by going with the definition that you're landed with. This is sort of at a point where you've still got quite a lot of flexibility to take advantage. And that can be, I mean, that's an interesting thing. I mean, part of, you know, getting a successful theory is getting the right definitions and knowing where to use the right sort of concepts to build a new concept. And that, I think, is something they've succeeded very well in this theory. So that said, I think we're at a point now where I can move on and start to look at applications. But before I get into sort of the large margin stuff that is really the main aim of what I'd like to do, I thought it was worth just making a connection with the VC dimension stuff to try and show you that we're not talking about something completely different, that there is a relationship between the Radamaca complexity of a function class, or rather the Radamaca function complexity of a VC class is sort of sensible in terms of the VC dimension. So I've got a few slides on this, and hopefully this also will provide a refresher for applying the kind of concentration inequalities that you've come to love this morning. Okay, so if we, so the idea here is we've got a VC class H, so you know it's got VC dimension D. And what we'd like to do is say, well, okay, we know it's sort of not got high capacity in this VC sense, but does that mean that it actually will have a low Radamaca complexity? Can we say something about the Radamaca complexity as a, you know, hopefully the Radamaca complexity will not be too high if it's a sensible measure of complexity. Because we certainly know if the VC dimension is low, we know we can learn. So, you know, it should be reflected in a measure of, like the Radamaca complexity. So what we can do is imagine just a particular function f, a fixed function f on the sample. Remember that in a VC class you could have lots and lots of, infinitely many functions, but once you restrict yourself to the sample, we know that there aren't that many because we have this bound on the growth function. But let's just focus in on one possible function for the time being. And what we can try and do is say, what is the chance that this is greater than or equal to epsilon? Using our sort of concentration mind, we observe that the expected value of this thing inside the absolute value, if we think of the randomization over the sigma I, the expected value is actually equal to 0. So now what happens, what I'm thinking here is the probability of a single instantiation. So I'm thinking, take a random sigma I, what is the probability that it's greater than or equal to epsilon? So the probability is here over the choice of the sigma i's. So we can apply the sort of, let's go back and remind ourselves what the Herfting or Radamaca, McDiarmid concentration things look like. So actually, if we probably go back to, no, let's go to the McDiarmid, it's probably easier. So the idea is that we're able to say something about the difference between the expected value of the function and the particular observation that we get when we take a random sample, in this case a random sigma I. And what I've just said is that the expected value is 0. So all we have to do really is work out the value ci, and we're going to just plug it in on the right-hand side. And if you remember, we could get 2 here, and we can get the absolute value. So we've got the probability that the actual observed sum sigma I greater than or equal to epsilon is less than this. So all we need to do is observe what the sigma I is, the ci is, and we'll be in business. So, it's just a refresher course on applying these things. Sorry, just get back to where we were. Okay, so what is the amount that we can change this sum if we substitute one xi with an alternative xi hat? We substitute a different value. Well, this is a binary classification function, so it can change by at most 2. It could have been +1, it might now be -1. So sigma I is equal to 2 over, 2. And so if we plug that in, we get actually, this was some sigma I, so we get, it should be maybe, it was 4m, that's right, but there was a 2 here and the 2 cancelled, so it's 1 over 2m. Okay, so that's all very easy. Yep, so now, as I mentioned, because it's a VC class, we can't have actually that many different functions on the sample. There are only BH, the growth function of m, different actual functions that you can get, and that is bounded by em over d to the d. So we're going to apply the union bound again, pull out the old tricks, and we're going to try and make the probability that any of these different functions is greater than or equal to epsilon, at most delta. So what I'm trying to do is say, look at this right-hand side, take the union bound over all the different f's, so I get in a factor here that adds up all these probabilities, and then I'm going to set this equal to delta and try and make that equality hold. So that's exactly what I've done there. I've put in the growth function, and that's the quantity, and I've set it equal to delta. And I'm going to choose delta to be m1 over m. We'll see why in a minute. Okay. And if we solve that, you can just invert this. You get the epsilon equals to this. Okay. Again, we get the square root coming in because we've got the epsilon squared there. We've got the log 1 over delta, but I've actually put the em. Sorry, no. Where's the? The delta was 1 over m. So yes, so that's okay. So it's all come out as we would expect. I won't bother to go through the detail. That's it. Okay, so now we can bound the Radamaca complexity in the following way. There are 2 possibilities. When we work out that sum, it might be bigger than epsilon. And the other possibility is that it's smaller than epsilon. Now, the probability that it's bigger than epsilon is delta. And the biggest it could be is m. So I've estimated the Radamaca complexity. 2 over m is from the front. You remember, it's 2 over m, the expected value of sigma of the sum. So this delta is the probability that it might be bigger than epsilon. And m is the size it could be if it's bigger than epsilon. That's sort of the worst case. And then with probability 1 minus delta, it's at most epsilon. Right? Epsilon was the thing I computed on the previous thing from this thing. Okay, so I'm making account of the fact that I worked out the probability that this thing could have been bigger than epsilon. I've got a particular epsilon and a particular probability here, and I've now just upper bounded the expectation based on those values. Okay, so delta is the probability it could be bigger than epsilon, in which case it's at most m. Otherwise, with 1 minus delta, it's epsilon. Okay, so now I just plug in. Now, delta I chose to be 1 over m, so that just becomes 1. So that's the 2 over m here. And I'm going to assume this 1 minus delta is just 1, and this is the epsilon that I computed. So if you look at that, it's actually very, very reminiscent of what we had when I showed you very briefly the loss version of the VC bound, where we allowed errors, training errors. And in fact, this will reconstruct that result for us exactly almost, because if you remember, the Radamaca bound has that form that it says the generalization error is the empirical error, that's just the number of errors on the training sample in this case, plus the Radamaca complexity, plus this little extra term, but we won't be too worried about that. I mean, that was also in the other VC bound. So we've actually reconstructed to within this small 2 on m here, which is really negligible, the actual, what I quoted as the sort of agnostic version of the packed bound, with non-zero loss. So that looks good. It looks like we're getting what we would hope to get out. In fact, we've got something slightly better here, because this was the empirical Radamaca complexity that we can use. And so the D here could be the D, the VC dimension, when we restrict the function class to the sample. So again, we're taking advantage of the fact that if we might have a high VC class, but the main probability mass is concentrated where the actual functions are far less, have a lower VC dimension. So that actually on the sample we might be getting away with a much lower VC dimension, whereas the previous theory was unable to deal with that. It had this idea of the soup over all possible choices of training set was taken as the definition of the VC dimension. So this could be here, if you like, the empirical VC dimension rather than the true VC dimension. So very nice. That's a sort of satisfying feeling that things are looking okay. So now I think it's time to move on, unless there are any questions on that previous thing. Do stop me if there are. To looking where I think Radamaca in a way comes into its own to a certain extent, the applications to large margin classification. And I think there are two main sort of achievements here. One is in the application to boosting, and the other is in SVMs. I'm going to spend most of the time talking about SVMs, but I would like to first look at the boosting case and show you how very nicely Radamaca complexity works in that case as well. So I'm going to claim that we can view boosting as seeking a function from the class which is a sum here over a linear combination of these weak learners that Gunnar has told you about. And I'm going to assume that they're closed under negation, so I can also assume that these coefficients are positive. I haven't written that down, but imagine it says AH greater than or equal to 0. And I'm going to assume that their sum, their one norm of those coefficients, is less than or equal to B. And I can describe that, I mean, denote that class as the convex hull with a coefficient of expansion b of the class of functions h, which is this class of weak learners. So essentially you can think of boosting as starting with a sort of a class which I call the weak learner class, which might be quite sort of constrained, and it moves to first taking all linear combinations of those functions and then sort of builds up to a slightly larger norm by maybe expanding those beyond the convex hull to a sort of expansion of that function class. So you would say, it's considerably expanding on the power of the weak learners by this freedom of allowing to take linear combinations of them. Now, typically the way you can see boosting algorithms as working is in some sense trying to minimize the one norm here of this of these coefficients, and that is why you tend to end up with sparse results unless you run AdaBoost for a very long time. But typically, you can end up with sparse, and if you actually cast it into a constrained optimization problem, I think this is probably the most natural way to do it. So you try and minimize the sum of these coefficients and perhaps some suitably weighted of the slack variables, where the slack variables are the amount by which the weighted combination fails to achieve margin 1. So it's very like a support vector machine definition here, but it actually has the one norm of the dual coefficients, if you're thinking in in support vector terms, and it has also the one norm of the slack variables. If you do this, you end up with something that is often referred to as linear programming boosting, and I'm sure that Gunnar has spoken about that or something similar, hopefully. If not, I mean, I guess I could talk about it at some point if people want me to. I could slot something in, but I think that's probably fairly clear. Okay, so it's a nice way of approaching learning. It ends, this one norm is typically a good way of forcing sparsity into a solution. So typically you end up with a sparse set of weak learners. But certainly, you've expanded considerably the power of the function class, it would appear. Okay, so that's the, yeah, Lorenzo. Yeah.
Do you minimize the function with the slack variables over the convex hull, or?
You minimize this over...
or just over H, or what, I don't know.
Over the choice of these and the choice of these. So it's just, min over A and psi. I should have AH greater than or equal to 0 here.
So there are no constraints on AH in the functional?
No constraints, no, apart from the fact that they're greater than or equal to 0 in this case, the way I've written it.
And it's equivalent to minimize it on the convex hull? I mean, is the...
okay, you could turn it around and say, okay, I'm going to constrain this sum to be 1 and I want to maximize the margin gamma, and I put a gamma in here and it will be the equivalent. It's a bit like, doing a canonical hyperplane or minimizing the margin but fixing the margin, you know what I mean? Minimizing the norm but fixing the margin. Yeah, sure, no problem. Is that okay? Yeah. Yes?
Is there any constraints on AH? Should it be non-negative?
Yes. Sorry, I mentioned that. There should be AH greater than or equal to 0 here. I'm assuming that the function, the weak learners are closed under negation, so that if h of x is in the class minus h of x. So there's no point in allowing negative AHs. It just simplifies our analysis, that's all. Okay? Yep. Any other questions? Okay, so this is sort of a reasonable way of viewing boosting, I think. So what we'd like to do now, okay, we've got a nice sort of learning algorithm and it seems to work quite well, and we'd like to apply some sort of analysis. So we wheel on Radamaca Complexity. And really what we need to do is to estimate the Radamaca Complexity of this class here. So that's what I'm going to try and do on the next slide. If I remembered the right order. Yeah, okay. Okay, so the Radamaca complexity of that class. Okay, so this is remarkably easy. So what is it? It's 2 over m. I'm going to do the empirical, the expected value over the random Radamaca variables of the soup. And now what we're doing is the soup of the function in this class, but I've just written out how we choose a function in this class. We choose it by first choosing an hj in h, and then a sum over j of aj less than or equal to b. So I'm assuming that we're allowing any number of these, so I haven't put a limit on how far j goes. And what we want to do is to make the sum sigma I equals 1 up to m, sum j, aj, hj of xi as large as possible. Okay, so that's just rewriting the definition of the empirical Radamaca complexity. So we're choosing the function from this class that maximizes the inner product with this random set of variables. Okay? Okay, so the first thing to observe is that we can bound this by taking the sum aj's outside and just taking the absolute values inside. It's just the triangle inequality. Now, once we do that, we observe that, okay, if we imagine choosing an hj to make this large, and then we choose another hj to make this large, it really is going to be the same hj. I mean, there's not going to be any point in having a different hj, because whichever h in h makes this the largest, we're going to choose all the time. Right? I mean, if you think of making this big, I mean, aj is a positive, so you want to make this as big as possible. So clearly you're going to choose the h that makes this the largest from within h, and there's not much else you can do, really, at that point. But once you've done that, that means that really you only need one j. You don't really need the others because they're all the same anyway. I mean, simply all you're going to do is choose the h which maximizes that sum. And so really you just can remove this altogether. And sorry, I should have got rid of the sub j here. It should be soup h in h without the sub j here of b times this quantity. But hey, wait a minute, that's just the Radamaca complexity of the function class h. So that's it. So effectively, what we're telling ourselves is that, so this is just b times the empirical Radamaca complexity of the function class h. Is everyone happy with that? I mean, it's almost sort of, so obvious that you think, wow, really? There must be something wrong. And what it corresponds to is because this thing, you're looking for a point, if you like, which has maximum correlation in a one-norm constrained class, and essentially it's always going to be one of the points of the polytope that is the furthest in the direction that you want. And that's what this is saying. Essentially, it's going to be one of the functions that does it. And so there's really no point in having this sum. Now, if we think of the case where b equals 1, that corresponds to taking the convex hull of the set of functions h. And what it's telling us is that moving from a set of functions to their convex hull does not increase the Radamaca complexity at all. That's really weird. I mean, you would think that you're vastly increasing the sort of functional complexity that you're involved with, and yet the Radamaca complexity does not increase. Of course, if you blow it up, it does by this factor of the blow up. So we've moved to the convex hull without incurring any complexity penalty for b equals 1. Okay, so that is a very, very nice property. And, it really sort of suggests that if you're doing any sort of learning with any sort of function class, if it's not closed under convex combinations, you might as well close it. It's probably going to make learning easier. It's almost certainly, it doesn't seem that it's going to make your sort of, if you like, complexity penalty any higher. And it's going to give you greater flexibility to do what you want to do because you've actually added, a whole lot of extra functions into your class. So I think this is a really interesting sort of conclusion to be drawn from this observation. And it sort of perhaps explains why boosting is such a good approach to learning, and why it does seem to be so resistant to overfitting. I mean, there is very great evidence now that obviously boosting can overfit, but it actually is remarkably resistant to overfitting. So, I think the Radamaca complexity in this case gives quite a lot of interesting insight. Of course, in any concrete case, you would still have to estimate the Radamaca complexity of the base weak learners, but often these are actually really quite simple. They might be, small trees or whatever. So anyway, that's all I was going to say on that score, and I think it's time to move on to the Radamaca complexity for SVMs, unless there are any questions on the boosting topic. Is that okay? Okay, so I think this is almost the penultimate, well, here's the penultimate thing I really want to talk about. This hopefully will show you sort of how the sort of technology of actually applying these techniques to something that's a little bit more complex than the boosting perhaps, and will also lead into the final example that I will try and fit in if I have time, which is to show an application of this to kernel PCA. So again, I'd like to try and give you at this stage a sense of how one might use this technology to understand some sort of algorithm that you're using. So if you like, this is a user guide, I hope, to applying Radamaca complexity to your favorite, algorithm or technique. We'll see how we go. There are some details that I probably will skip over, but I was hoping to give you, if you like, a sort of, feeling you'd taken the trip right through and seen, all the details. I may not succeed in that, but I certainly hope to give you a good, clean feeling of how it all fits together. Okay, so let's see where we're starting here. The functions that we're using are these ones. I'm writing them in this dual form, sum alpha I kappa, which I'm thinking of a kernel xi comma x, where we have this bound on the 2 norm of the weight vector, so we can embed that into the linear functions in the kernel-defined feature space. It's a subset of these functions where the 2 norm is less than or equal to b, and I'm going to call that function class f sub b. Okay, so I've assumed this kernel is a Mercer kernel, whatever you want, a positive definite kernel that Bernard was talking about, so that it corresponds to an embedding in a feature space. Okay, so this is the first sort of step, which is to bound the Radamaca complexity of that function class f sub b. Okay, this will only be the first step because we're still going to have to put it together to actually get the margin type of bound. So this is, we'll see how that works, but this is a sort of first stage, which is bounding the Radamaca complexity of the underlying function class. We're then going to have to go to look at the loss function, but let's look at this first. Okay, and this actually again turns out to be remarkably, well, it looks bad, but it's not actually that bad. So let's start. Here we are. This is the definition of the Radamaca complexity. Soup over this choice of function in this function class f sub b, 2 over m, the inner product. That's we're getting familiar with that. And now I'm just going to recall that this is a linear function in this feature space defined in this way. So here's the weight vector, and I've actually taken this sum inside the inner product, so that this would be w comma phi of xi, and I've taken the sum inside and applied it here. So this is w comma 2 over m sum sigma I phi of xi. Okay, so that's, and the constraint that puts us into this class is that the norm of the weight vector should be b. So that's just a rewrite of this top line in terms of the the representation of the class. Okay. Now we can use here Cauchy-Schwarz inequality, because this is less than or equal to the norm of the weight vector times the norm of this vector. Okay? So the norm of the weight vector we know is at most b, and I've taken that b outside, and I've taken the 2 over m outside, so that becomes 2b over m here. And so this is just then the norm of sigma I phi of xi that we have left. So that is just the Cauchy-Schwarz, but actually that's very, very tight because, or exact in fact, because if you wanted to choose the W to maximize this inner product, you would choose it parallel to this guy, and then Cauchy-Schwarz is actually an inequality. So in fact, that's equality there. So we haven't lost anything yet. Now I'm going to do something, this is a little bit hard to manipulate, so what I'm going to do is write it as the square of this, followed by the square root, and the square we can write as the inner product with itself. Okay, so this is taking that norm squared, write it as an inner product with itself, and then take the square root. And once we've done that, we can take the square root outside the expectation, and we will increase it because the square root is a concave function. So I have this way of sort of drawing diagrams to try and convince myself when I have something like that, am I allowed to do it or not? Will that work? Sorry, this is the high-tech version as opposed to the Microsoft solution. Okay. So if you have the square root function that's concave, if you look at 2 points and you compute the average of those values, it will be less than or equal to what you do if you take the average and then compute the square root. So if you think of these 2 points, you see here's the average of those 2 points. That's the square root of the average. That's the average of the square roots, so that they increase because it's a concave function. I mean, it's the standard sort of thing. So that implies that we can move that square root through the expectation here, and we're going to increase the value of the function. Okay, and now we've got this quantity here. Now this is very, okay, so then I've observed that this inner product here can be written by taking the sums outside of the inner product. You've got the sum over ij, sigma I, sigma j, and then you've got the inner product 5xi, 5xj, which is just called the kernel, okay? So now the very nice thing here is the expectation of this. What you get is all of the mixed terms, sigma I, sigma j, where I is not equal to j, have equal probability of all 4 possible values. So they could be 1, 1, 1 minus 1, minus 1, 1, or minus 1, minus 1 with equal probability. Okay? And so when we take the expectation, those cancel out because 2 of them are equal to plus 1 and 2 of them are equal to minus 1. They all have equal probability, and so they cancel. Okay? So all the cross terms here go away. It's fine. Okay? And so all we're left with is the ones where I and j are the same, and then you get sigma I squared here, which is always equal to 1, because sigma I is plus or minus 1. And so the sigma i's actually disappear completely, the randomness disappears completely, and we're left with just the sum I equals 1 up to m of the inner product between xi and itself in the feature space. Okay? Is everyone happy with that? The cross terms here, when we're taking the expectation, they're equal probable, all combinations. 2 are plus 1 plus, I mean, 2 of them are equal to plus 1, the plus 1 plus 1 case and the minus 1 minus 1 case. 2 are equal to minus 1, the plus 1 minus 1 and the minus 1 plus 1. So, you know, in 2 cases you have plus kappa xi xj, in 2 cases you have minus kappa xi xj, and they all cancel out. It relies on the symmetry, of course, of the kernel. Okay? So you're left with this quantity here. So the Radamaca complexity of the linear function class is just the trace of the kernel matrix, square root of that, 2b over m. And that's actually very tight. There's very little. The only real inequality that we used was this one here due to the concavity of the square root. This, I say, should be really an equality. And so this is actually a very tight path. Okay. Okay, so now we're in a position to move towards application of this, and we're going to try and apply it in the one norm SVM case. So recall that what we have here is, I've actually turned this around slightly And I'm going to define the S1 norm SVM in this way, which is sort of more equivalent to the new SVM actually, but for different values of C, they'll be equivalent. So I'm minimizing minus the margin plus C times this slack variable sum, where the output, the margin of the examples, is greater than or equal to gamma minus the slack variable here. So it's a slightly different, and I'm constraining the weight vector to have norm 1. So it's, normally one sort of minimizes the weight vector squared, but it's an equivalent but different way of formulating it. Okay, so what I'm going to look at now, how are we doing for time? Just a few more minutes. Okay, so what I just want to convince you that of this notation here, and that will set us up. So psi I here can be written as y minus g, yi g of xi. That's just turning around this constraint here. If you look at the psi I, you can write it as this function, which I'm writing as g. This part here I'm going to write as g of the xi. So this is yi g of xi is just this quantity here. So gamma is, psi I is equal to gamma minus that, and plus here because the psi I is assumed to be greater than or equal to 0. So you have to cut off if this goes negative. Okay. So that's just a way of writing psi I. And if we take the Heaviside function on minus y of g of x, so the Heaviside function is 1 if this quantity is positive and 0 if it's negative. So yg of x measures the margin. So if the margin is positive, this is negative, then that's the loss. Sorry, that's 0 in that case, because we've got correct classification, and if this is yg of x is negative, this is positive, and we get a 1, which corresponds to a misclassification, and that therefore gives us the binary error, the discrete error, and that's the probability of misclassification. Okay, so it's just getting a little bit of the technical details around down in this notation. Okay, is everyone happy with that formulation? Okay. So let's take a break there, and we'll come back and pick up, and we'll be in shape for the finish.